Well, good morning or good afternoon. This is Mr. Kinney. We're going to go over this year's 2018 and 19 Unit 2 test questions. I'm going to do many of the calculations. I'll set them up with you. So, coming over here, number 1, grams is a measure of, well, that's going to be mass. Milliliters and cubic centimeters are a measure of volume. And let's see, grams per milliliter and grams per cubic centimeter, that's going to be a measure of density. This equation triangle right here, what I really like about equation triangles, usually you kind of set them up like this, but whatever you're looking for, if you're looking for density, cover up the D, and it tells you it's mass divided by volume. If the problem gives you density and mass and it asks you to calculate volume, you cover up the V and it's mass divided by density. If you happen to be looking for mass in a problem and they give you the density and volume, this shows you that you multiply those. So it's a nice little trick. This will not be on the test. We'll have the equation density equals mass divided by volume. Make that a V. You just need to make sure you know how to use it. So on this particular problem, you're just going to have to multiply these together. Length times width times height. And I think when we do that, it comes out, I'm not going to tell you there's going to be a number, 0.765 is what I got on my computer. Now we want to round this to 1 decimal place, so be careful, pay attention. So that'll be still that number, but if we're going to 1 decimal place to the tenths, that means that this 6 is going to pop that to an 8, and that these would be cubic centimeters because we're doing centimeter times centimeter times centimeter. Cubic centimeter. Number 3. So if the box from above, and we're talking the one we just did the calculation, has this mass, excuse me, what's the density? Pardon me. Well, density equals mass divided by volume, and, oh, I'm going to sneeze. Excuse me. Yes, bless me. Okay. I just had an almond and it kind of dried in my throat. The mass in this problem is 430 grams. The volume we had up here from the other problem is going to be something, 0.8 centimeters cubed. And when you get the answer here, we need to round it to 1 decimal place. So you make sure you'll have, pardon me, sorry about that. Just round it to 1 decimal place just like we did above. It'll be a point something answer. Number 4. So we're giving you have 3.1 gram samples of aluminum. Okay, I'm just going to put Al, that's its symbol. We have iron. Its periodic table symbol is Fe for ferrum, and gold, Au for aurum, or aura. You know, they say some people have a glowing personality, they have a nice aura. Anyway, Au. So we're given all those, and we're saying we have 3.1 grams of each, 3.1 grams of each. So I'm just going to put 3.1 grams, just to remind me that I have 3.1 grams of each of these. Calculate their volumes. So we have a couple of ways we can do that. We can rearrange this equation here, the density equals mass divided by volume, and we're looking for volume. So one way we can do it, volume is going to be the mass divided by the density. So the mass in this problem, each of these, so for aluminum, this is the aluminum part, we have 3.1 grams of aluminum, and we're going to divide it, because we said that volume is mass divided by the density equals, sorry for squeezing that in. So we got 3.1 grams as our mass, and we're going to divide it by the density of aluminum, which we set up here was 2.7 grams per cubic centimeter. The grams cancel out, and you'll get your answer there. I'm not going to tell you that. Now, we could have done it the conversion method. So the other way we could have done it, let me draw a line here. We put the given. In this particular problem, we were given 3.1 grams of aluminum. We'll put that over 1. And now we're going to do a conversion here. So this is our quantity. The relationship is that, we want grams to be in the denominator. So 2.7 grams of aluminum is 1 cubic centimeter of aluminum. The grams cancel out. And we have the same thing we had up here, okay? We've got 3.1 divided by 2.7. Two different ways. Do the iron, it's going to work out just the same way. Volume equals mass divided by density. The mass of the iron was 3.1 grams of Fe divided by the volume in this problem. I'm sorry, we're looking for the volume. This was supposed to be D down here, my mistake. Volume is mass divided by density. Corrected myself, glad I caught that. So the mass is still 3.1. The density for iron, 7.9 grams per cubic centimeter. Or you could set it up, the given is the mass, 3.1 grams of Fe over 1. And then the conversion factor says that we have 7.9 grams of Fe and 1 centimeter cubed of Fe. And it turns out either method will get you the right answer. And yeah, the last one. By this time, it should just be kind of practice here. But let's get that over so we can see it. Okay, volume is mass divided by density. We're getting that from rearranging the density equation, either algebraically or if you make yourself a simple little equation triangle. Wait, mass divided by density. Oh, I'm still hung up on putting the actual. There we go. Mass divided by density. Volume, mass divided by density. And let's see, the mass is still 3.1 grams of gold divided by the density of gold, a whopping 19.3 grams per centimeter cubed. Or you can do it the conversion factor method. You put the given over 1. We were given 3.1 grams of gold, and then the conversion factor is the density. We know that there's 19.3 grams of gold in every 1 cubic centimeter of gold. And there you go. You can do your own calculations. I won't do that. Okay, you have a 700-gram chunk of pumice. Here we go. I got little samples I brought in that we'll practice with. So here's a piece of pumice. This is a volcanic rock. A whole bunch of little, it's almost like nature's styrofoam, rock styrofoam, really lightweight. And in fact, with this, if I put this in water, it would float, and that kind of matches the density there. 0.3 grams is what they're saying there. So anyway, let's see what our problem is. You have a 7,000 gram chunk, that's mass. I'm just gonna, and I recommend, when you're reading your test questions, do this. Density, okay, they give us the density. We're looking for volume. So that's what we're trying, oh, let me get this up here. Holy cow, sorry everybody. I don't have my students here to tell me, hey, I can't see it. So going through 7,000 grams, I label that M. It gives us the density, and it asks us to calculate volume. So just like we did in this one, volume is still the mass divided by the density. So that's one way we can do this, and we can put the mass of 7,000 grams of pumice divided by the, hold it, doggone it, Richard, volume is mass divided by density. Equation triangle, mass divided by density, we rearrange it. The density of pumice was 0.3 grams per cubic centimeter. Make sure I'm back zeroed, I am. And at that point, you can do the math. Now, the other way is to say you do the conversion method, 7,000 grams over 1 of pumice. And the conversion factor is 0.3. We want to get rid of the grams. So 0.3 grams of pumice is 1 cubic centimeter of pumice. So there you go. Okay, we have a chunk of frozen lava. Okay, I went and collected these. Here's a nice little piece of basalt. Also, that's also another type. We can call it another type. It's obsidian. I don't know if you can see the shininess on there. Let me add some light to this. There we go. Volcanic rock. Anyway, so there's some volcanic rocks. Pumice is also volcanic rock. So let's see. we have, can we see that up there? We have, this is our volume, 219 cubic centimeters of frozen lava. We got the density. Mass is equal to what? So density is equal to mass divided by volume. We want the mass. If we multiply both sides by V, we'll find out that mass is going to be volume times density. If we use the equation triangle, we cover up the M on the equation triangle. It is going to be density times volume, which we just figured out. So that's the way we can do it using the equation. So let's put in the volume, 219 cubic centimeters of lava. And we're going to multiply that by the density of this lava, 3.2 grams of lava in 1 cubic centimeter of lava. You've got your answer. Or you can do it the conversion factor method. The given 219 cubic centimeters, over 1. That's our given. That's of lava. And we're going to multiply that by a conversion factor. We want to get grams, so we need 3.2 grams in the numerator of lava is 1 cubic centimeter of lava. And that lets us cancel these out. And we're set up. Lastly, you have 300 milliliters. That's a volume of molten lava with this mass right here. What's the density? Okay, this one, we just got to use the density equation. Density is the mass divided by the volume. That's a given on the test. Mass is 1,050 grams of lava divided by 300 milliliters of lava. And the density is going to end up being, well, it's going to be, what's 1,000 divided by 300? It's going to be close to 2 or 3-ish is what I'm guesstimating. Number 8. Scoot on over here. So for this one, how many centimeters are in 600 meters? Well, let's put our given over 1. This is a conversion factor, 600 meters over 1. And then we got to multiply that by the relationships, by the factors given. And you can do, let's see, we can look on our chart right over here. Well, actually at the top of our review sheet it says that, let's see, what do we got? Well, it doesn't have what a kilogram, but oh, do we not have that one on there? Oh, so what we're going to have to do is, we don't have kilometers listed on there, but we do have this chart right here. And actually, you should know that kilo means 1,000, sorry. So we could say that there's 1,000. Let's just go by what we have on our charts here. For this one, we're looking for centimeters. Oh, my goof, we do have that. I think that is on here. Do we have that 1 meter is 100 centimeters? Sorry about that. I was getting a little mixed up there. So I'm looking just on the top of this chart right there. So I'm going to put that relationship. I'm going to say, because I want meters down here and centimeters up here. There's 1 meter is 100 centimeters. And you can do the math that way on there. And then let's see, the next one coming across here, it says part B. Let me zoom out. How many kilometers? So we can do it like this. We can start from the beginning and do 600 meters again over 1. And let's see, kilometers to, now you know what? I didn't have that listed up there on that chart. Darn, I didn't have that. Oh, yeah, we do. Yeah, my mistake. 1 kilometer is 1,000 meters. So we want meters down here, kilometers. And that conversion factor was that it's 1 kilometer is 1,000 meters. So 1 kilometer is 1,000 meters. And those will cancel out, so we set it up right, and then that way that'll get you your conversion over there. Convert 60 grams into kilograms. So there's a couple ways you can do that. We could do, first off, our given grams over 1. And we can look on the chart up there, and it'll say, well, it doesn't give us a direct grams to kilograms conversion. on there. But if we change this to 1 kilogram would equal 1,000 grams, you can do that as well. Or we can look at our chart right here. So I think the first one I'm going to do, I'm just going to go on here and saying, okay, 1,000 grams is 1 kilogram. So on the test, when we give you these values like this, we may not give you like kilometers, kiloliters, and kilograms, but you can change that from meters to grams or even into liters if you need, like we did there. Or we can use this little chart, which you'll have on the test as well. You could have, or 60 grams over 1. And we want to cancel grams here, and we want kilograms up there. So if you look on here, let's see, 1 gram is going to be 0.001 kilograms. So we could do 0.001 kilograms is 1 gram. And those two will give us the same value either way. So whatever your answer was here, okay, so you got some answer there, we got to convert that into pounds. So we'll take your answer there. I'll just circle it. Okay, that's going to be some number of kilograms over 1. And we want to convert it into pounds, and it says right here that 1 kilogram is 2.2 pounds. So we want to have kilograms in the denominator and pounds up here. And I think it said it was 2.2 pounds is 1 kilogram. So whatever your given was from over here, you're going to multiply it by there. And let's see, if you are 51 inches tall, how far is that in centimeters? Well, 51 inches over 1. And the conversion factor up at the top says that there's 1 inch is 2.54 centimeters. So we want inches down there, centimeters up here. And I think it said it was 1 inch is 2.54 centimeters. So now once you get your answer for that, over here, that's going to become the given over there. So that becomes the given here, number of centimeters over 1. And then we want to go from centimeters to millimeters. So here's centimeters on here. There's 100 centimeters in 1,000 millimeters. So it's so we want centimeters down here and millimeters up there. And then for centimeter, there's 100 centimeters in 1,000 millimeters. Those will cancel out, and you got your answer. Okay, now we're on the back side of the paper. And let's see what we got here. How are we doing on time on this? 18 minutes. This is going okay. Draw the 3 states of matter. Show spacing. Okay, well, for solids, they need to be really close together and usually drawn in some type of a packed order. And let's see, solids, liquids. Liquids are really close together, but they're not necessarily locked into any particular order. Now, they can move a little bit, so I'm putting short arrows in here. These guys can vibrate. I'm just going to put squiggly lines to represent, I'll just even write vibrate. And then liquid, L-I-Q-U-I-D. And then let's see, we got gases. They're going to be far apart. And they move quite a bit. They move very fast. Now let's see. Kinetic energy is the same as speed or motion. So these have high kinetic energy, middle or mid kinetic energy. Kinetic energy is speed. Also, it can be directly related to temperatures too. And then this will have low kinetic energy between there. So we do everything. Show spacing, yes. Motion, yes. And whether they're, okay, did that. Okay, a beaker of water is being heated on a Bunsen burner. So here's a Bunsen burner. Wanted you to draw that. Okay, there's going up. Here's the beaker diagram, convection flow. Let me get my red pen as well. So wherever it gets hot, when it heats up the water, it's going to make, the water gets hot, they're going to expand, it becomes low density. Low D, low density here. As it gets to the top of whatever material it's in, it begins to cool off. In a boiling container of water, it becomes steam. When in the mantle of the earth, it hits the crust and cools off. And as it cools off, it gets denser. So it becomes cool and dense. I'll say denser. These are also going down, so we've got a nice convection current drawn. So over here, I'm going to put the water drops kind of really close together because they're denser. Those same 9 water drops over here, now I'm exaggerating, but they're going to be a little bit further apart. They're not into a gas yet, they're still liquids, but they're just further apart. So this is going to be the low density because the atoms spread apart. Higher density because the atoms are closer together. All right, draw a diagram of the Earth. Okay, well, I'm just going to kind of do a partial one there. We've got the core, the outer core, and then we got most of this is the mantle. Then we got like the crust of the Earth there. This isn't necessarily a scale. Label the inner core. Okay, this is IC. Inner core. Wait, I'm sorry. Inner core right there. This is the outer core. And the outer core, let's see, draw the convection currents in the mantle, and this is mantle. Please tell me I'm focused on there still. We are. Let me zoom in some more. Okay, so we've got heating from the core in the mantle making this stuff, the magma and stuff, get hot and rise. It hits the crust and it cools down and it sinks, and you get these little convection currents. Now this heat is coming from the outer core. I should have had this drawn in another spot. But you've got heat rising from the inner core, and then it gives up some of its heat to the mantle, and then it cools down, and we've got this convection current going on in the inner core, or the outer core, excuse me. So, and naturally right here, if you've got the motion of the Earth, these are going to tend to be pushed this way. They'd call that a divergent boundary, pushing it apart. And you're going to tend to get volcanoes, or even like the Mid-Atlantic Ridge and stuff. Even part of Africa from Saudi Arabia is right at one of these points, and parts of Africa and Saudi Arabia are moving apart from each other. Put these in scientific notation. Okay, first off, 2.03 times 10 to the, so we always make it 2 point something on that one. This is number, let me get the numbers there so you can see them, fast forwarding through. And since we'd have to go 2 this way, plus 2, because it's bigger than 1. Now this one I goofed up. This should have been 23, but anyway, 2.00003 times 10 to the, okay, so 1, 2, 3, 4, 5. You'd have to move the decimal 5 places to get it back from where we had to move it there. Okay, this one here, 2.03 times 10. Now this number's smaller than 1, so it'll be a negative exponent. And that decimal place went 1, 2, 3, 4 places. 203. Okay, 0.0. Well, that's just going to be like that one, except it's going to be 2.3030 times 10 to the 2. We'll just have an extra significant figure. Over here, 2.03 times 10. Now this is smaller than 1, so negative exponent there. And let's see, 2 places is what we had to move it. Negative 2 places. And lastly, 2.0 becomes 2.0 times 10 to the, actually it's 10 to the 0, okay, because that's just 1, so sorry, I won't stick you on that. Now, let's see, significant figures in these. So let's see, in this one right here, 3 significant figures. Over here in this one, okay, we had 1, 2, 3, 4, 5, 6 significant figures. Over here, those zeros don't count, so we just have 3 from the 203. Over here, this 0 is important because it's telling us we're being accurate to the 10th place, so that's going to be 4 places. This 0 is just a placeholder, so it's just those 3 numbers. And over here, we have just these 2 numbers. That 0 is important because it's telling us we're being accurate to a tenth there, so 2 there. Put these into standard notation. Okay, so 6022. I'm just rewriting this times 10 to the 2. Now that's going to be number big, so I got to move the decimal over 2. So it's going to end up between 1, 2, between these guys right there. Okay, this one, 602. First write out the number. Now negative 3. So I got to move the decimal. We got to be smaller than 1. 1, 2, 3 places. 1, 2, 3 places. So it'll be 0.00602. This one here, okay, 76022. Now that's times 10 to the 5. So and the decimal place was right here. So 1, 2, 3, 4, 5. I shouldn't have given that to you in unscientific notation, but that's the way it is. So that's going to become, I think, 7,602,000, so on. And over here, 7602, now it's times 10 to the minus 4. So that decimal has to go this way because we're going to end up with a number smaller than 1. So we end up like that. Okay, I want you to draw open and closed systems and isolated. Okay, I'm just going to draw circles here. Open, okay, matter, and I said draw arrows for energy flows. Okay, so matter, okay, so I said dotted lines for matter. This is matter coming in and out. Okay, so this is open. We'd have like a little lid on there. So this is matter. And then I said energy can flow in and out of an open system. So matter goes in and out. Over here we wanted a closed system. Now matter, let's see, matters are dotted ones. They're trapped inside in a closed system, but heat can still come in and out, or other types of energy. So this is closed. And this is our isolated system. In theory, okay, the matter is trapped in there. That's supposed to be my dotted lines. And energy is also trapped in there. So this would be isolated. Isolated. There we go. I think I did that. Correct. And lastly, okay, for each types above, well, this could be like, okay, an open system. This could be like a cup of coffee or soda, or even like, okay, a glass drink, okay, glass drink. Drink in a glass, cup of coffee cup. Okay, it's open at the top. Steam can go out, or you can pour stuff in. Closed system, this would be like a sealed thermos or a sealed bottle. When you get your soda at the store in a bottle, it's sealed bottle. You still see that? And I can't quite read my chicken scratch, but oh well. And isolated, okay, this is only in theory. As close as we can really get might be like a really good, an excellent thermos, like a Yeti or something. An excellent thermos. But these don't actually exist because energy really can somehow get in and out. Lastly, down here, determine the densities by comparing their volumes. I'm just going to say that these blocks have a volume of 1. Volume equals 1. I'll just say cubic centimeter, just like we practice in class. And I'm going to say each of those little dots is 1 gram. Okay, equals 1 gram. So if we do that, this is going to be 3.8 over 1 for the density. This would be 6 over 1 for its density. 0.8 over 1. 1.2 over 1. This is like we had a starter. It was like this. This one over here, 3 over 1. Uh-oh. This box is about twice as big. So I'm going to say the volume of this one, volume equals 2. There's 4 dots in it, so mass equals 4. So 4 divided by 2 equals 2, so density equals 2 on this one. This one over here is about 3 of these boxes. So volume equals about 3 compared to the other ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we got mass equals 9. 9 divided by 3 is, I think it's 3. So density equals 3 on that one, okay? So then we might give questions like on the test, okay, which one of these would, let's say, would sink in a liquid with density that equals, well, let's say 1.0. So which of these would sink in a liquid with a density of 1? Well, any of the, I think all of these would actually end up sinking except C, all but C. C would float. How about which would sink in a liquid with a density equal 3.1? Okay, so now anything with a density less than 3.1, okay, this would sink. A. That one would definitely sink. B. That one wouldn't. That'd float. This would float. 3. Oh, that'd float. This one here, even though it's bigger, but its density is only 2, it would float. This one's density is 3. It would float. So I think if I got this right, just 3 of them would float. The other ones would all sink. All right, we're done.